Hi, everyone. I can't leave the Fibonacci numbers without mentioning its surprising applications in nature. Sunflower petals, numbers of petals, pine cone and seashell patterns. If there's time, I hope to be able to email out a link to Art Benjamin's TED Talk on the Fibonacci sequence. It's fascinating. All right, off to summation or sigma notation. We're taking the leap to series. All right. So basically, this symbol here is the uppercase Greek letter sigma. If you've taken statistics, you remember his little brother. Lowercase sigma stands for standard deviation, a measure of spread in data. The big brother, uppercase sigma, stands for summation. It's a summation operator. So we use it to efficiently indicate the addition of terms. We take the sum of terms in a sequence. That's why this stuff's here, because we often add up terms in a sequence. So for example, evaluate the following finite sum. All right, in calculus, we care more about infinite sums, but for right now, let's get started with finite sums and get used to this notation. I here is the index of summation. It's the counter for the terms, right? We start with I used k or n before. We use I also. I could equal 1, 2, 3, or so forth, right? Here, actually, we start with I equals 0, actually, come to think of it. Here we start with I equals 0. I mean, if you can't see this, I could be 0, 1, 2, 3, and so forth. In fact, you'll find that in like differential equations, you can get negative numbers here. All right, anyway, so we're going to consider a sub 0, actually. A sub 0, in a way, is our initial term that we're considering, right? I here is the index of summation. Sometimes j is used, k is used, n could be used. But I here does not mean the imaginary unit. Remember, we're keeping things real. So we can think of I as a dummy variable in the sense that it's like it's like your new coworker. If you replace one dummy with another, nothing never ever changes, right? If you replace I with J, K, N, whatever, you're going to get the same result. If you replace one dummy with another, nothing ever changes. Some people say that about politicians. All right. So summation, I equals 0. That's the lower limit of summation, the 0 here. In pre-calculus, you often start with 1, but I'm being cute here. I'm starting with 0. And remember, in calculus, you often start with 0. 3 here is the upper limit of summation. And in fact, I'm going to take away the ... Basically, I'm indicating that we're going to want to plug in all the integers from I equals 0 to I equals 3. So I'm eventually going to plug in each of these values of I into this expression here. Here, a sub I equals 5i squared minus 1. So what we're going to do is we're going to successively plug in 0 to get a sub 0, 1 to get a sub 1, 2 to get a sub 2, 3 to get a sub 3, and do what with the results? Add them using the summation operator. All right. So always, whenever you see this, summation I equals 0 to 3 of a sub I, it always, always, always means this. A sub 0 plus a sub 1 plus a sub 2 plus a sub 3. Again, you're plugging in the integers from 0 to 3, one by one, and then you're adding the results. So when you plug in these values for I, when you evaluate a sub 0, and a sub 1, and a sub 2, and a sub 3, okay? Remember, it was 5i squared minus 1. Here we have 5 times 0 squared minus 1, 5 times 1 squared minus 1, 5 times 2 squared minus 1, 5 times 3 squared minus 1. Remember, you're adding these, okay? So if you want partial credit on something, make sure you put these plus symbols. In fact, I think it's a good idea to at least show this work. I realize that this is a lot of writing, and in fact, I don't require you to write this out on homework or exams. However, I do expect you to write this, okay? You should work out what these terms are, indicate the summation, indicate the plus signs, right? Okay. And of course, give the final answer. A sub 0 is -1, A sub 1 is 4, A sub 2 is 19, A sub 3 is 44. In some cases, there are certain cancellations you can exploit where you can be cute, but it's usually most straightforward to work out these terms individually, okay, and then add them all up. The sum of these is 66. So we've evaluated the sum. Now this is a finite sum where we get used to the notation. What happens if we add up infinitely many terms? Okay, now just in general, a series arises when we take the sum of terms of a sequence. So kind of like what we did before, except here I'm starting with 1, and I'm changing the index to k. That's fine. Here's an example of a finite series. You see this a lot. Summation from k equals 1 to n of a sub k, which is a sub 1 plus a sub 2. I'm assuming n is kind of big. A sub 1 plus a sub 2 plus a sub 3 plus yada, 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 plus a sub n. I assume that n is a positive integer. This is an example of a finite series. And in fact, later on, we're going to call this S sub n, the nth partial sum. This is going to be the nth partial sum, which is the cumulative sum, kind of like the running total, of the first n terms of a sequence or series. Okay. Where we start with the first one, starting with k equals 1 or whatever, right? So if you start with k equals 1, this is very clear. Otherwise, it might be a bit muddy. So this is the nth partial sum, S sub n. It's the cumulative sum of the first n terms of a sequence or a series. Okay, like an infinite series. Starting with a sub 1. Now, finite series, we worked out the sum of a finite series here. So these things represent a series, but here we evaluate the sum of a finite series. You can think of this as evaluating the sum of a finite series. The idea of a series is more conceptual. It's like the idea of adding terms. This up here was a finite series. So for a finite series, you can evaluate the sum, and the result is typically a number in a basic problem. But finite series aren't as interesting as infinite series. Summation k equals 1 to infinity, a sub k, which is a sub 1 plus a sub 2 plus a sub 3 plus yada, yada, yada. The finite series above, okay, again, I just mentioned this, the nth partial sum. This is the nth partial sum of this infinite series. Imagine a sequence from a sub 1 on forever, a sub 1, a sub 2, a sub 3, with infinitely many terms, okay? Now, see, the idea of an infinite series is that it's the concept of taking these terms and adding them all up. A sub 1 plus a sub 2 plus a sub 3 plus da-da-da. It's an attempt to add infinitely many terms. But this infinite series may or may not actually have a sum. So when we talk about a series, we're basically representing a sum of terms. But actually, the sum itself may or may not exist. The series may or may not actually have a sum. By definition, a sum is a finite value. It's not infinity or negative infinity. And we're going to talk more about the idea of infinite series having a sum later. More in 9.3. Next up, we're going to talk about particular types of sequences and series. We're going to categorize them. Some very important ones.